Hi and welcome to another tutorial video. In this tutorial video what I'm going to be doing is showing you how to use Prim's algorithm. And what Prim's algorithm does is it allows us to find a subgraph of a weighted graph which is of minimum total weight. And I'll show you what that means in a moment. And that's often called a minimum spanning tree. Okay, so let's get into the steps of the algorithm then. Okay, so these are the steps of the algorithm, and to start off with, what we've got to do is we've got to choose a node in our original graph that we're going to start at, and we connect it to its closest neighbour in the weighted graph. Then, second of all, we connect the nearest node to the minimum spanning tree up to the minimum spanning tree. So we're building up a minimum spanning tree here. And the second step of our algorithm is to find the next closest node to the minimum spanning tree that we've got so far and connect it to the minimum spanning tree. Then we repeat that step until all of the nodes are connected to the minimum spanning tree. Okay, so what I'm going to do now is go through an example which will hopefully make this a lot clearer. Okay, so what I've got here is a weighted graph. So let's first of all choose A as our starting node. So I'll write down A in our new minimum spanning tree over here. And the first step of our algorithm is to connect A with its closest neighbour. So we look on our original graph and see, well, the closest neighbour that A has is B because it's got two neighbours, B and D, and the weight on the edge from A to B is 1 and the weight on the edge from A to D is 5, so we'll connect A to B. Then we've got to connect the nearest node to the minimum spanning tree, so that means that we've got to look at all of the neighbours of A and B and see which is the closest. So we can see that A has a neighbour D, which isn't in our minimum spanning tree yet, and that's got a weight of 5. B has a neighbour D as well, which has a weight of 6, and B also has a neighbour E, which has a weight of 8, and B also has a neighbour C with a weight of 2. So the smallest of those distances there is the distance between B and C, which is 2, so we're going to connect that. Then we have to repeat that step because we've still got D, E and F from our original graph which aren't connected to the minimum spanning tree. So what we have to look at are all of the edges that connect A, B and C to D, E and F in our original graph and see which is the smallest. So we've got these 4 edges here. The edge from A to D, the edge from B to D, the edge from B to E, the edge from C to F. And which one is the smallest? Well, that will be the edge from C to F, which is the smallest weight of 3. So we're going to connect C to F. Then we've got to repeat that step because we've still got D and E which aren't connected to our minimum spanning tree. So we have a look at all of the edges that are connecting F, C, B and A to D and E, and that is the edge from A to D, which is 5, that is the edge from B to D, which is 6, the edge from B to E, which is 8, and the edge from F to E, which is 2. So the smallest weight on any of those edges is the 2 from F to E, so we're going to connect that edge. And finally then we need to connect D to our minimum spanning tree, and we have a look at all of the edges that are connecting D to the other nodes in our original graph, so that's this edge, and this edge. We see which is the smallest, and that's going to be the edge from A to D, which has a weight of 5, so we connect that one. And that's why it's really important to not just look at the edges that are connecting the node that you've just connected to the unconnected nodes. You have to look at the edges that are connecting all of the nodes that are currently in your minimum spanning tree to all of the nodes that are not currently in your minimum spanning tree in order to get the minimum total weight. Okay, so that's our minimum spanning tree, and we know that we finished now because all of the nodes that are in our original graph are in this minimum spanning tree and are connected to all of the other nodes. And the total weight for this minimum spanning tree is 13. Okay, so here's a further example of a weighted graph that I'm going to show you how to do Prim's algorithm on. So I'm going to start off at the vertex A, and the first step in our algorithm is I've got to choose a starting node and connect it to its closest neighbour. So I'm starting at A, and the closest neighbour to A is E. So this is the start of our minimum spanning tree. Then I've got to connect the nearest node to the minimum spanning tree, and the nearest other node to our minimum spanning tree is B, because we can go E to B at a weight of 2. Then the next nearest node, we've got a choice. We can choose either to go from E to F or E to G. I'm going to choose E to G. Then the next closest node in our minimum spanning tree is going to be E to F, because that's a cost of 3, and we could either have gone G to D at a cost of 4, E to F at a cost of 3, B to C at a cost of 7. Then the next closest node to our minimum spanning tree is C, because that's a cost of 3. We could have either gone F to C at a cost of 3, B to C at a cost of 7, or G to D at a cost of 4. And then finally, the next closest node is D, and we can the minimum cost for going to D is C to D at a cost of 1, because we could have gone G to D at a cost of 4 or C to D at a cost of 1. So we're going to go C to D, and that gives us our minimum spanning tree, and the total edge weight of that is 14. So that's just another example of how you use Prim's algorithm to generate a minimum spanning tree. Okay, so I hope you found this video useful, and thanks for watching.